For decades, biology has taught us one strict rule. To get oxygen, you need sunlight. Through a process called photosynthesis, plants harvest light from the sun to manufacture the gas that keeps every animal on Earth alive. Because of that rule, we make a logical assumption about the deep ocean. Down in the absolute darkness of the abyss, no light means no plants. Therefore, breathable oxygen down there must be imported, carried by ocean currents from the sunlit surface above. That brings us to the Clarion-Clipperton Zone in the Pacific Ocean. This specific stretch of seabed sits 4,000 meters down. To reach it, you would have to stack half of Mount Everest vertically into a trench. At this extreme depth, the environment is completely cut off from the sun. According to the foundational laws of biology, generating brand new oxygen down here should be physically impossible. In 2013, a marine ecologist named Andrew Sweetman dropped a robotic lander into this pitch-black water to run an experiment. The lander was designed to sink to the absolute bottom and capture a sealed, isolated chamber containing nothing but a tiny patch of the seabed and the saltwater immediately above it. Take a look at this chart plotting oxygen levels over time. Based on basic biology, the trajectory was obvious. Because the trapped microscopic organisms continued breathing, oxygen was projected to steadily drop. But instead of falling, the line shot the other way, surging steadily higher day after day. This put the research team in a difficult position. Either a multi-million-dollar piece of sensory equipment was totally broken, or a core law of Earth science was being defied in real time. Sweetman took the practical route. He assumed the sensor was faulty and ignored the anomalous data for almost 10 years. But in 2021 and 2022, his team returned to the Pacific. They ran the exact same drop sequence with brand new, differently calibrated hardware, and they got the exact same upward curve. The equipment was flawless. Down in the freezing dark, trapped in a tiny box cut off from the surface, fresh oxygen was spontaneously appearing. They knew the microscopic animals in the water were only consuming gas, and there were no plants available to make more. The only variable left inside that chamber was the ocean floor itself and the peculiar rocks scattered across it. The Clarion-Clipperton seabed is covered in strange potato-sized mineral deposits known as polymetallic nodules. To find out what role these rocks played, the team brought samples up to their ship. They placed them in a completely dark, refrigerated laboratory to perfectly recreate the freezing pressure of the abyss. The nodules operate like natural batteries. They emit a localized electrical charge into the water, triggering seawater electrolysis. The current strikes an H2O molecule, breaking its chemical bonds and forcing the hydrogen out. The isolated atom left behind is raw, breathable oxygen. Because this creation process bypasses sunlight entirely, scientists have given it a specific name, dark oxygen. There is a lingering mystery to the mechanics. In laboratory settings, the internal charge of the rocks eventually depletes, halting the oxygen production entirely. We still don't know exactly what recharges them in the wild. Regardless of the power source, the hard data remains. Lifeless, static rocks are actively manufacturing the exact gas required to sustain biology in the darkest place on the planet. The immediate consequence of this data is that photosynthesis has lost its monopoly. Biology is no longer the strict prerequisite for making oxygen. Basic geochemistry, the physical reaction between dead minerals and salt water, is now a proven, independent engine for it. This forces researchers to look at the Earth's history through a new lens. If these metallic batteries have been splitting water molecules in the dark for millions of years, they could have easily been bubbling up oxygen long before the first plant evolved on the surface. If that timeline holds true, the estimated date for when oxygen first filled our atmosphere is no longer strictly tethered to the appearance of the first plant. We have operated on the assumption that life began in the warm, sunlit shallows because that was the only place oxygen could exist. But if dark oxygen was abundant 4,000 meters down, the first microscopic forms of life could have sparked into existence in the pitch black. And if it happened here, it changes the math for astrobiology. When we search for life on the dark, ice-crusted ocean moons of Jupiter and Saturn, we no longer need to find sunlight to prove the water is breathable. We often view the deep ocean as a hostile wasteland, far removed from the vital processes of the surface. Instead, we now have evidence that this darkness provided the oxygen necessary for the very first aerobic life to emerge.